So suppose you have an 11-sided die, or actually don't, because 11-sided dice are kind of hard to find. So suppose instead that you need an 11-sided die, but you're luckily equipped with a beautiful dodecahedral 12-sided die, like this one. Anyway, so yeah, you have your 12-sided die and you want to simulate an 11-sided die. Luckily you know how to do this. The construction works like this. In order to roll the 11-sided die, you roll the 12-sided die until you get something which is not a 12. That is the result of your 11-sided die. So it's clear from this definition that the probability of getting a face other than 12 is equal to the probability of getting a different face other than 12. Like, the other faces are all symmetric. And the probability of eventually getting a 12 is 0 because you're not supposed to return if you have a 12. You're supposed to roll again. From this, it's immediate. There are 11 equal probabilities of getting the faces 1 through 11. They all add up to 1, so each probability must be 1/11th, which is exactly what we want it to be in order to simulate an 11-sided die that's fair. So, the probability of getting 1, as I just said, is 1 in 11, but in fact we can also write down another expression which expresses the probability of getting 1, and this will show that this other expression is equal to 1/11th. So it goes like this. We consider the different ways that we could arrive at a 1. We could roll the 12-sided die and get a 1 on our very first go. This has probability 1/12. Or we could do something different. We could get a 12 the first time, have to roll again, and then get a 1 on the second time. Independent events of the probabilities multiply. Or we could do something else different. We could get a 12 the first 2 times, 1/12 times 1/12 there, and then get a 1 the third time, etc., etc. 1/11th is equal to 1/12 plus a 12th squared plus a 12th cubed plus etc., etc. So this is this interesting algebraic, or arguably not algebraic because there are no variables, but it's clearly an identity of some sort, and you can argue that it becomes an algebraic identity when you realize that this analysis works not just with our particular 12 and 11, but in fact, if you have any n-sided die and you want to simulate any n minus k-sided die, you can do a similar thing and get your result. The problem with this is, if you can call it a problem, that n and k are sort of restricted to being integers. It's not clear, at least to me, what a 3.5-sided die would actually do when you rolled it. So it becomes limited in scope because you can't talk about numbers which are not integers or reciprocals of integers or rational numbers. Ideally you'd want a version that works for any real number. Luckily, you can do this because in probability theory we have a very convenient place for real numbers to fit in. Real numbers are probabilities. So suppose you have an unfair coin and it's tails with probability p. When you flip it, there's a probability p, which is any real number between 0 and 1 of being tails. It follows then that since edge is not an allowable outcome, the probability of getting heads is 1 minus p. Again, probabilities of disjoint exhaustive events have to add up to 1. So, probability of heads is 1 minus p. We can use this coin to play a certain game. The game goes like this. If you flip the coin and get a heads, then the game ends. If you flip the coin and get a tails, then you flip the coin again. The game starts by you flipping the coin. So you flip, tails, flip, heads. Okay, the game's done. That was a typical result. The probability of the game finishing is 1, and here I'd like to take a quick digression into what probability 1 actually means. Does this mean that it's guaranteed that the game will finish? Well, you can maybe imagine always getting tails, but that wouldn't strike you as particularly likely. And in fact, the probability of that is 0, because if you get a tails n times, that has probability of only p to the n, and as n goes to infinity, this goes to 0. So the probability of always getting tails has to be 0, and maybe that's possible, but it's infinitely unlikely, or really whether it's possible starts to depend on, can you do infinitely many things? in a finite amount of time, or maybe in an infinite amount of time, and it starts getting into physics, which is neither algebra nor probability, really, although, of course, it relates to both. So let's just say that the probability is 1, and accept that as good enough of a termination condition for our game. But like before, it's not just a 1, it's the probability of termination, and the probability of termination is also something else, so this 1 is not just a 1, it's also something else. And we can find what the something else is by doing the sort of case-by-case analysis like before. How can the game end? Well, we could just get a heads the first time, that has probably 1 minus p, or we could get a tails and then a heads, so p times 1 minus p, or we could get 2 tails, p squared, and then heads 1 minus p, plus etc., etc. If you want to clean it up a bit, depending on what you find as simplified in terms of algebra, you may rewrite it by dividing by 1 minus p and get something like this. 1 over 1 minus p equals p to the 0 plus p to the 1 plus p to the 2 plus etc., etc., etc. This is the familiar geometric series formula for the sum of an infinite geometric series, which some of you have possibly seen before. And I think it's really cool that it's possible to derive this simply by considering an unfair coin, or the limited version, you consider a die simulating another die. For people who care about convergence, we've really only proved this in the case where p is between 0 and 1, and in fact, it doesn't work when p equals 1. It might be instructive to go back and see exactly where our analysis fails in that case, but negative values of p, negative probabilities, don't make a ton of sense at the moment, and for p larger than 1, this on the right is clearly divergent, if you know what that means, so it's not surprising that our analysis breaks. But it's a really cool, I think this may be one of my favorite proofs of the geometric series formula, and it's entirely through probability theory. Thanks for watching.